Let's start our session with a conductor first. So today we will discuss about the conductor sizing and selection. So let me share you my screen. So today we are discussing about the conductor. So let's first of all let's go through our SLD first, and again we'll come back to here. Just as a recap, see here, this is our SLD. We discussed it in our last session. So these are the 33 kV feeders, 10 number of 33 kV feeders connecting to 2 metering base, and they are pulling to the 33 kV bus bar with sectionalizer and connecting to 2 transformers, and then the metering section and the 2 lines of 220 kV going out from the my substation to the grid substation. And if you remember, if you just recall our last discussions, the bus bar configuration which we adopted in the 220 kV is a double main with coupler scheme, and in 33 kV it is a single bus with sectionalizer scheme. So now we are having all these equipments which are already tabulated here. Let me see, these are all the equipments like breaker, lightning arrestor, isolator, and CVTs, bus potential transformer, current transformers. So these are the equipments which are existing, or the mandatory equipments we are focusing on for our today's for the next our classes. So these are the equipments. Now we are much focusing on each and every equipment. So let's start for today's session. Let's start with the conductor. So if you see from the starting, there should be some intermediate connection is required, which we are connecting the lightning arrestor and the isolator, CT, breaker, and isolator onto the bus. So this bus again a conductor, and the connections which is between the lightning arrestor, isolator, for all this again we required some conductor. We required a conductor. So now in our today's class, we are discussing about different types of conductor and how to select the conductor. How to select the conductor. How the conductor will work. How the conductor will function. Let's see that. Let's go to the again our presentation. Just to have some basic look on the conductor first. So what is a conductor? A conductor represents the most important component of the overhead power line, because they have to ensure economical and reliable transmission to contribute considerable to the total line costs. So just read the some important terms in this sentence. One, I am talking about the economical. The word I am talking about the reliable, and these two I have to ensure the economically, and that should be reliability, which leads to the total line cost. Total line cost. In the sense, suppose in our earlier discussions also I told you that when we are selecting any equipment, could be a conductor, breaker, or a transformer, so we have to choose an equipment that should be economically viable to my application, and also that should be reliable in terms of operation. So we have to select a conductor or any scheme that should be techno commercially viable one, means that should have a good reliability as well as it should have a less cost, means cost. So if you are moving towards the high reliable, obviously the cost will be high. If you look for the price less cost, obviously the reliability will be low. So we have to choose this optimal point where my system will suits for a best economical and a best reliable. So The conductor we have to choose that should be both economically and reliably viable. And that leads to my total line costs. Total line cost here, the cost of the line, the capital cost, and also the losses. The losses also very important factor when you are selecting the conductor. If the conductor resistance is very high, obviously the line losses will be high. The line losses will be high, right? So when you are selecting the conductor, these are some considerations also we have to take into the consideration to select a conductor. So let's go in a simple way. Come to this part. So how to select and how to size the conductor? Generally, in the market, we are having a wide range of conductors. Different types of conductors are there in the outside market, but we are much focusing on some of the conductors. Like suppose we all well known about the conductor called ACSR. ACSR is aluminum conductor steel reinforced. Aluminum conductor steel reinforced. This is a one type of conductor. ACSR is a one type of conductor. What is a type of a conductor? Let's see. You can send the power from one end to other end through some medium. So this material that should be having high conductivity of electricity. So that material should be a copper, that material should be iron, that material should be whatever it may be, aluminum. So whatever it may be, if you want, you can choose. But by taking some considerations of some factors of corrosion, weight, and other things, flexibility, and the strength of the conductor, everything, generally, and cost, everything, all the conductors are made of aluminum. All the conductors, transmission line conductors, are made of aluminum with aluminum material. So on the aluminum material, from the aluminum, we are having different types of conductors. Like some, we know this family, ACSR family, where aluminum conductor, some small strands will be there. We will call these are the aluminum strands. And in the middle, we are having the steel strands, steel. Why we are placing the steel in the middle? Just to make the high strength due to the wind loads or due to the ice loads, etc. To give a good strength for the conductor. Having the steel content inside it, the resistivity of this conductor is high. And this aluminum steel reinforced conductor or having or can be withstand for low temperatures, means up to like 75, 85 degrees Celsius or maximum 90 degrees Celsius. It seems that the conductor temperature, what the relation between the conductor and the temperature. Let's see this. If I am sending some 5 amps through this conductor, maybe due to this 5 amps and the resistance of this conductor and how much time it is flowing on this, some heat will be developed inside this conductor with a form, you know that formula is I square RT, heat losses. Okay. This heat losses, this heat will rise the conductor temperature from the ambient outside temperature. Suppose the ambient temperature in that region present is 40 degrees Celsius, but due to the flow of 5 amps in this conductor, the conductor temperature is 60 degrees Celsius. Is suppose a 60 degrees Celsius. The conductor temperature in the sense I am injecting 5 amps through that conductor. When I am injecting 5 amps, based on this resistance and the time of flow, everything, the conductor temperature rises to 60 degrees Celsius. When the 60 degrees Celsius is the conductor temperature, so now when I am injecting 10 amps in this conductor, the temperature is rising to, suppose, 85 degrees Celsius. And if you are adding the current of 15 amps in this conductor, the current is rising to 110 degrees Celsius. 110 degrees Celsius. So this process will occur based on the current flow, because the current is S square. Mostly it is depending or inversely proportional to the square of the current. So the temperatures are mostly depending on the factor of current. So when you are injecting the current, if you are increasing the current, the temperature of the conductor is boosting up. So up to which level? So I designed a conductor, and I am sending the current in this 1 amp, 2 amp, 3 amp. So it is okay, it is working. But when it is reaching to the 5 amps, I noticed that the conductor broken down, damaged. Because when I am injecting 5 amps of the current, the conductor temperature is rising to 120 degrees. 120 degrees Celsius of the conductor temperature, the material cannot withstand 120 degrees of Celsius. So my conductor came into the breakdown. So then I will say that, oh, the selected conductor can carry current of 4 amps only. Can carry a current of 4 amps only. Okay. I will talk that. Be with me for some time, Sujan. Okay, 4 amps only. 1 amps, 2 amps, 4 amps. So 4 amps is the limit for my selected conductor. How I selected this? Based on the temperature effect. Based on the temperature effect. So we got an idea that the current carrying capacity of the conductor is related to the conductor withstand, the temperature withstand capacity of the conductor. So the first point, when you are selecting or sizing the conductor, we have to check these 3 things: the current carrying capacity of the conductor, the short circuit current withstand capacity of the conductor, and the techno-commercial, that should be techno-commercially viable. So if I am just focusing on the first 2 statements, the current carrying capacity of the conductor is directly proportional to the temperature withstand capacity of the conductor. So if you select a material, if you are designing the conductor with a high that can be capable to withstand high temperatures, so you can send much more power in that conductor. That is the concept of HTLS, high temperature low sag conductors. Now we can see so many conductors. Okay, let's see that in a while. So this is just a brief introduction of the conductor now. So now let's talk about how to size the conductor. The sizing of the conductor, can be the sizing of the conductor will be done with 2 things. One is the current carrying capacity, other one is the short circuit withstand capacity. So now let's talk about the current carrying capacity. Wait a minute, I will share you this. Oh, sorry. Yes. See, our team, are you able to see my screen? Yes. So generally the conductor sizing, the selection or the conductor sizing will be done as per the standard of IEEE 738. So what in this is, so I said, we have to choose what is the current carrying capacity of that conductor, current carrying capacity of the conductor, and the second one is short circuit withstand capacity of that conductor. These two will be done by two methods. One is a steady state calculation, which will tell the current carrying capacity of the conductor, and the second one is short circuit current. This we will do at transient state condition. Transient state condition. Steady state and transient state condition. So what is the steady state and what is this transient state condition? And what are the inputs we need, we required to develop this conductor sizing? So let's talk in this way. First of all, to do the steady state thermal rating, we need to first of all assume the first step we will assume is the conductor. We have to assume the conductor temperature. We are assuming some conductor temperature like 50 degrees or 60 degrees, whatever it may be. Conductor temperature. And next, we are calculating the corresponding heat losses. We are calculating the corresponding heat losses with a formula we already discussed, I square RT. Right? Now, next, now after calculating this, now I am calculating the conductor temperature, conductor current that yields this conductor temperature using some equation. That equation we will call as a steady state heat balance equation. Steady state heat balance equation. By using this steady state heat balance equation, I am calculating the what is the current is flowing in this conductor. Steady state heat balance equation. What is this steady state heat balance equation? Generally, simple way. Now what is happening? Now a heat is developing in the conductor. Now let's assume if the heat developed is equal to the heat gained by that conductor due to the flow of the current. If this is equal to the heat losses, or maybe which is satisfying with the convection or radiation losses, maybe this heat will be dissipated out, maybe in the method of convection or radiation. If both are in balance, if my ohmic loss generation is equal to the heat losses of convection or radiation, so whatever heat is producing, it is dissipating out. Then it's creating some balanced kind of steady state. So at this condition, I am calculating the current. So that I can say, oh, this is the current which will flow on based on this temperature. Now I am calculating the calculated current. Now I am comparing this calculated current with the given conductor current by the manufacturer or in the as per the standards, whatever it may be. Given conductor current. Now I will increase my conductor temperature or decrease the conductor temperature until the current equals to the given current. Until the current given equals to the given conductor current. So this is the work I will do to calculate what is the conductor current. It's kind of a derating effect. Now, in a simple way, as per some standards or the tables, we can see, I will show you in the next minutes, where you can see 400 square mm of conductor will carry 850 amps at 75 degrees Celsius. But this is a standard one. If you take that and if you are applying at your application in your substation, this substation is located in the northern hemisphere and the temperature is less, and if the wind speed is good and the wind direction, everything is having a good thing, then obviously those will acting as a cooling agents to your conductor, conductor. So the conductor can carry more than the given conductor current. Means that temperature, the temperature you are looking at. It's in simple. Suppose if I arrange some coolers on here, the conductor, what will happen? I am cooling down this. So you can pump more of current. More of current. You want to dissipate that heat. So we cannot place the coolers on the transmission line. It's not possible. So what we have to do? So that has a natural convention, like the heat which is dissipating through the ohmic, that should be which generating through this ohmic losses, that should be equal to this convention on radiation heat losses. So by this, we will calculate the current using a formula like I equal to root over QC plus QR minus QS solar heat gain by resistance of the conductor at assumed temperature, whatever temperature you assume that. So this will give you the exact current. So now this QC, QR, QS, we have to calculate. These we are having so many much big formulas are there. I will share you that worksheet guide. There you can see this. But in a brief, this is the application for the current to calculate the current carrying capacity in the steady state condition. Fine team, clear till now? Got my points? Yes, no, please. Yeah, thank you. So this is the way of steady state approach. And again, I am just telling you for who are preparing for the interviews, some of the candidates, just I am giving the current carrying capacity, the conductor sizing, the current carrying capacity will be done as per the IEEE 738. So we have to focus on two things. One is what is the current carrying capacity of the conductor, and the second one is how much short circuit current that conductor can withstand. So to do this, to perform the current carrying capacity, to know what is the current carrying capacity of that conductor under your geographical or conditions on your wind speed or a solar radiation, latitude, longitude, all this will come into the picture. All this you are calculating this. You have to do the steady state thermal steady state the calculation. In the steady state calculation, the first thing is I am assuming some conductor temperature. I am calculating the heat losses, and I am calculating the conductor temperature that yields this conductor current that yields this conductor temperature using the steady state heat balance equation, which is I equal to root over QC plus QR minus QS by a resistance of that conductor temperature C. Then I am comparing that calculated current with the given current. So now to match this given current with the conductor current, you can increase or decrease the temperature. So now if your temperature is falling below the withstanding capacity of the temperature, then it's fine. If it is more than that, then you have to go for the next size of the conductor, it seems. This is a simple way of doing the steady state calculation to know the current carrying capacity. And the second approach is short circuit calculation. Short circuit calculation in the sense, we already discussed this in our first classes. For every voltage, could be at 33 kV, for 220 kV, we are having some standard short circuit ratings. for 33 kV, 25 kiloamps or 31.5 kiloamps, and for 220 kV, it's a 40 kiloamps. So all the equipments are designed for 40 kiloamps or 31.5 kiloamps, whatever it may be. So you are and you have to. This is a conductor which is also one of the part of your substation. So you have to ensure that this conductor can also withstand for that short circuit current for some duration. And also you have to know what is the transient thermal rating that your conductor will get when the temperature, when the current is rising from like simple normal rating to the short circuit at a step range. So that we are doing in the transient calculation. Generally, these transient calculations will be done using some MATLAB works. In a simple way, let's see this concept and I will again discuss in a practical way. Let's see the short circuit one. So generally, this is my one. This is the current. This is the current, and this is the time. This is the time. Now, generally, my standard current, which is my I1, this is a normal rated current, is flowing in this direction. And after some time, there is a occurrence of a fault current. So step rise, right? Obviously, there is a step rise in the fault current. So this is the fault current, which is continuous for some time, So due to this step change in the fault current, the conductor temperature also, in the normal period, it is a initial temperature. After this, due to the rise in this, the temperature will not rise at a single time. So based on that heat dissipation, it is having a gradual rise like this, and it reaches to the final conductor temperature. This is the final conductor temperature. It is rising like in a curve way, not in a step. So with some linearity, it is rising up. And it reaches to the maximum temperature, the maximum final temperature. Suppose, let's assume, during this case, during the time less than 0 minute or 0 seconds, the conductor is assumed in the thermal equilibrium. I mean that the ohmic losses which is generating by the conductor is equal to the heat losses of convection and radiation. And after that, due to the change in the current, a step change in the current, so the conductor temperature is unchanged rapidly, but the rate of the generation of the ohmic losses will rise. And it is following some equation. This equation we will call as a non-steady state equilibrium balance equation. Non-steady state equation. So that was derived again in the IEEE 738. Non-steady state balance equation. Means by just with change in the step of the current, the temperature is also changing, but not as rapidly as the current. It is having some equation which is following, that is a non-steady state equation. So now let's assume in a simple way that I am giving an example. This actually we cannot perform with some calculations. We have to do some graphical things for this. So we need to do this in the MATLAB software or any other software, so which are used for this transient analysis. There you can perform this. But as a rule of thumb, we cannot always perform this. Okay, fine. Let's see. This is the work we will perform generally using some software. So because the transient analysis cannot be done. So now let's assume, suppose I am having a conductor like a Panther conductor or any conductor which is having a 400 square now. So that conductor temperature is Tc, and time, this is my time, conductor temperature, and this is the time. Now I am talking about the thermal ratings of the conductor. Now, when I inject a suppose 1,000 amps in that conductor, so the current is flowing like this. The 1,000 amps. This is 1,000 amps. When I inject in that conductor, the temperature is rising like this. The temperature is rising with respect to the time. With respect to the, this is the curve I am talking about. The temperature is rising with respect to the curve. And when I am injecting 2,000 amps, then the conductor, the temperature is rising like this. So based on this, we will check how much time this current, how much time that it will withstand. Suppose this is a 115 degrees Celsius, 115 degrees Celsius. To carry this 1,000 amps, suppose this is a 115 degrees is the worst condition of the conductor temperature, and this is my initial temperature, could be like 85 degrees or 80 degrees. So how much time it is taking? Like suppose a 15 minutes or 16 minutes. So I can say that my conductor can carry 1,000 amps of the current up to only 15 minutes. Similarly, if you use other cases of 40K or 25K, then you can see a significant decrease in this time. So it can like that, it will withstand only for 1 second or less than 1 second in this sense. So this is analysis by injecting the current. What is the rate of change of the temperature? What is the rate of change of temperature based on the rate of change of in the current? So this rate of change of temperature again depends upon the time. So we are calculating how much time it will withstand for this change in the temperature. That we are checking in the transient analysis. In a simple way, as a rule of thumb, if you forget all these things, in a simple way, we are having this formula that I have shown you in the here. This is the formula. For aluminum conductor, ISC root T by root over of 0.125 into log 10 of theta 2 plus 228 by theta 1 plus 228. Theta 1 is the initial temperature. And if you inject whatever the current, suppose of 40 kA, then you know that by injecting this 40 kA, what is the temperature rise by some graphs or maybe dou. So by this, you will come to know that the square mm of the conductor required. In a simple way, if you ask me, we will do with a formula like ISC root T by K. By this, suppose we will assume the K as 94 or 97 as a factor for aluminum. For time being, let's assume 97. I remember it's 97. So ISC, what is it for 220 kV? 220 kV, the fault current is 40 kA. And how much time you want to withstand? I want the conductor to withstand for 1 second, then divide by 97. So 40 into 1, obviously 1, divided by 97. So for just for simple calculation, I am assuming it as 100. So 40 by 100. So 400 square mm is the minimum requirement of the conductor to withstand this. This is the way of doing it. So it seems that the minimum size of the conductor required in a 220 kV level to withstand 40 kiloamps of current for 1 second, the minimum square mm is 400 square. That is the way of representation in the 220K with respect to the short circuit current. Make sense, team? Understood? It's a rule of thumb. Again, as in a normal way, we have to do the transient analysis using suppose softwares or whatever it may be. In a practice, generally for 220 kV, we will use the conductor Moose, Jebra, what I will discuss in the next one, and 33 kV Panther. So we are having some standards, some standard conductors. We are using those standard conductors for these voltage levels, for specific voltage levels. Clear, team? Any doubts still now? Team, are you with me? Yes, fine. Wow, cool. Thanks. So this is the way of doing the sizing and selection of the conductor team. So now in a case, generally, let's see what are the different types of conductors. Software in the sense, generally we are having MATLAB programs to do this, and transient analysis. I think in the ETAP we are having this. I'm not sure about this. I guess. Okay. So come to this conductor stream. We are having different types of conductors, like aluminum. This is the aluminum conductor, steel reinforced. For aluminum conductors, there are a number of different designs in use, have highest conductivity for given cross-section area. However, they possess only a low mechanical strength, which limits their application to short spans and low tensile forces. Aluminum conductors without steel, I am talking about. When you are using a steel, it is having a good mechanical strength that you will do the support to that. We are having different types of conductors. And when you are in a simple way, when we are selecting the conductor stream, we are having some guidelines to select this. Let's go to that one. So this is the one of the some standard ACSR family. Now let's see. We will talk this conductors here with respect to the name stream, like mole, squirrel, rabbit, dog, leopard, coyote, wolf, lynx, panther, as well as up to the Westmeans. And these are the square MMs available in the market. These are the square MMs. Like 10 square mm conductor, we will name it as a mole. And 130 square mm conductor, we will call that as a leopard. Instead of calling 130 square mm ACSR conductor, we will call it as a leopard, ACSR leopard, ACSR panther. ACSR panther can carry 467 or 487 amps at 75 degrees. Beyond that, it is not applicable because the maximum current carrying capacity that can be withstand by that ACSR panther is only 75 degrees. So that is a maximum. So at 75 degrees, you can pump only 487. So 487 is the ampere rating of my panther conductor. So these are already given a table. So you can select the current carrying capacity by seeing the tables also. By seeing the tables also, we will take these considerations. So you can